Inclined planes. Very common occurrences, not planes. Planes. Very common occurrences. Inclined planes. In lots of physics problems, and in life, lots of things take place on slopes or hills. And so we're going to look at how our free body diagram looks differently first, and then we'll talk about how we use some of the math to work it out. So if we were to draw a free body diagram of an object on level ground, then the object would have a certain mass, which we usually stick inside there. And then we can talk about the different forces that apply. There would be a force here called the normal, which is in response to the gravity that's pulling down. So in the y direction, we have Fg and the normal force. Gravity pulls down and the ground pushes up. And unless the question specifies that the object is moving, accelerating upwards or downwards, these forces usually end up being balanced. But you can have more than these. This is just the simplest version. We'll start with this, then we'll look at examples later where you have extra up and down forces that might change the normal force, and that's just extra calculating. Let's see. We usually have some sort of force that's being applied to the object to make it move, so we commonly have an applied force. And we often have a frictional force or some sort of resistive force working against us. Now, a lot of students think that every scenario has to have these four forces on it, but they don't. This is just the most common situation. Sometimes there may not be an applied force, or there may not be friction, or there may be extra forces added in. There could be a monkey pulling with a string, there could be a balloon attached, there could be something pulling up or down. But I just want to show you the basic idea of how it changes for the inclined plane. All right, now let's look at what happens if we put all of this on a hill. Let's draw our incline. And it really doesn't matter whether you draw the inclining up to the right or inclining down to the right. It's just the same picture reversed. Usually when we do an inclined plane, we want to have some indication as to how much the incline is. So there's usually an angle given. Let's just pick our favorite 30 degrees. And let's put our little box up here on the inclined plane. If we start drawing our forces in, well, the easiest one to draw is gravity because it never changes. Gravity is always down, but down is this way, Fg. The normal force is always perpendicular to the surface. That's what the word normal actually means in math. It means perpendicular. So the normal force is not going to be opposite the gravity. It's going to be perpendicular to the surface and pushing up this way, which looks a little different now than what we had in the other picture. We can still have some sort of applied force. So we can put an applied force. However, the applied force could be pulling up or down the hill. So let's just assume we have the applied force on this side to show the difference between this picture and the other one. Now the question is, would you have friction? Well, yes, you would, but which way does the friction go? Well, friction always opposes the motion. So when you look at this picture, you're not really sure if the block is going to be going up the hill or down, because gravity in this picture is doing two things. It's pulling downward, which means that some of it is pulling along this line here, down the hill. That's what makes things slide down hills. It's just gravity. Even if you let go of it and don't touch it, if the hill is steep enough, things will automatically slide down, because some of this gravity, this red line, is pulling down the hill, and some of it is pulling into the hill. And so you can see how this becomes more complicated. And our strategy is going to be focused on these two components, this component here and this component right here. And we'll use gravity in terms of components instead of the red line. Now, if this if this purple component right here is actually bigger than the force that's applied, then the gravity would win and the box would slide down the hill. But if the force applied happens to be bigger than that gravity component, well, then the box would go up the hill. And so we're stuck putting our force of friction in here without really knowing where it would go. So we first need to figure out which way the block is going to move before we can draw an arrow for our force of friction. But we know that it exists. We know it's there. So you can see how this becomes a little more complicated. So that's how the pictures would look. Let's look at how we might apply some math. So let's take the simplest type of question with an inclined plane. And rather than write it out in words, these are often easier just to draw. So let's take an object that's sitting on an incline, and we'll use 30 degrees. And we'll put this object right here, and we'll give it a mass of 50 kilograms. Actually, you know what? I just realized that I want to make this a little bit bigger than 30. 30 degrees is not much of a slope. We want to make sure that this thing is going to slide. So let's make it 50. All right? In fact, let's make it 60, because that way we can have nice, easy trig functions. So 60 degrees. This doesn't look like 60 degrees, but that doesn't matter. It's not the picture that you're following, it's the mass. So here's 50 kilograms of mass. Right? And I'll just erase this other from the previous picture so it doesn't interfere. Let's draw our free body diagram. Let's draw in the forces. Well, the force of gravity is always straight down. So I'll draw a vector representing the force of gravity straight down. And I will put Fg beside it. There will be a normal force pushing perpendicular to the surface. So I can put the normal force here. And in this scenario, let's just make a point of saying that there is no applied force. Nobody's going to push or pull this block. We're just going to set it there, and we're going to see what happens. No applied force. And we would also need to know a little bit about the friction. So let's say that the coefficient of friction, which tells us sort of how sticky the surfaces are, is going to be 0.1. And remember, coefficient of friction from last year. So I guess the question we can ask ourselves is, will the box or the block slide down the hill or not? Will the block slide? And if it does slide, then what will be the acceleration rate at which it slides? Because it will accelerate if there's a net force. Right? Or maybe it will turn out that it slides at a constant speed. Who knows what we'll find out when we actually work this out. Okay. So, what do we do with our math? You'll notice that the two vectors are not nice and clean in the sense that the gravity vector is straight up and down, but the normal vector is at a weird angle. And whenever we have weird angles, we need to do what we call resolving into components. So one of the ways that you can think about an inclined plane is to take your standard x-axis, right? Your standard x-axis and y-axis, your Cartesian plane looks like this. But if you twist it and tilt it a little bit, you can tilt it to look like this. So what we'll do is we'll take our x and y-axis and we'll tilt it so that it fits onto the inclined plane. So the x-axis now becomes the surface of the inclined plane. So let's just put a little, let me get it different here. Let's just put a tiny little reference line here to show that that's now our x and y axis. We tilted it to match the plane. So now whenever we talk about vertical forces, we're talking about forces in the x and y direction. Or sorry, the y direction. So we're talking about forces that are moving up and down this way. And whenever we talk about forces that are horizontal from here on in, we're talking about forces that are going up and down the ramp. So we've adjusted our reference frame to suit the picture. Gravity no longer falls on our reference frame. It's no longer a vertical force. So what we're going to do is we're going to turn it into two components. We're going to find the component that is in line with our new y-axis, and of course the other component which is in line with our new x-axis. And remember, these two lines have to be at right angles to each other. And we've talked about how we find the components of vectors like this. We need an angle though. An angle is going to be needed. So let's do a quick little bit of trigonometric exercise here. If we look at the triangle, which is formed by this line here, through here, and up here, then we see that we have a 90-degree angle down in this corner, and a 60, and since all the angles have to add to 180, we know that the angle up here is 30 degrees. All right, now, we also know that if we take the angle from our inclined plane, our new x-axis, and we look at the angle from here to here to the actual component of the gravity, that's a 90-degree angle. But we know that part of that angle is 30, which means the other part of that angle must be 60 degrees. So we've discovered that the angle inside the triangle is exactly the same as the angle of the inclined plane in this case. That's convenient to know. All right, now we can write expressions for our gravity. Fg is mg. So if I go down here in red and I write Fg equals mg, then we have numbers for that. It's 50 times 9.8, which would be 490, right? 490 newtons of gravity, the weight of the block. That means that the sides, or the components of this triangle, are 490, and this would be cos theta in this case because it's adjacent to my 60-degree angle. So 490 cos 60 and 490 sine 60. So you see how we're using the same idea. We use this with projectiles. We used it to simplify the initial velocity of a projectile, remember? And express it in terms of x and y. We're doing the same thing here. Now that I've got these two lines, I can figure out these numbers because they're actually just numbers. And so if we go sine 60 is a half, no, cos 60 is a half, sorry. So this number right here would come out to 245. Circle around it. And sine 60 is about 0.87-ish. So when you multiply that by 490, you get around 424. So this means that the gravity force is pulling into the slope at 245 newtons, and it's pulling down the slope at 424 newtons. That's what the gravity is doing. We now know how much of the gravity is pulling down the slope and how much is pulling into the slope. And so we can use that for our next step. Let's now draw our Fnet equations. Let's start with our Fnet y equation. Well, Fnet y is the sum of all the forces that are uppy-downy, or vertical. In our new picture, vertical is this way. Remember, we have adjusted our reference frame. So we have two forces that would fall on that line. One is the normal force, and one is the component of gravity pointing in the other direction, the 245. I'm going to first call that something before I put the number in. I'm going to call it FGY, the Y component of gravity. And there's nothing else up and down. The red line of gravity that was originally there, we don't even look at that anymore because we have expressed it as the sum of two other vectors. So it kind of disappears from the picture at this point. We never want to include that force anymore. We've rewritten it in terms of the two green vectors. If we put in our numbers that we've got, well, Fnet Y is either going to be two things. It's going to be MA, but if the A happens to be 0, it'll work out to 0. And in this case, we can see that the block is not going to move in this direction. If the block's going to move at all, it's going to slide down the hill, which is the x direction. So we know that if there is no acceleration, then ma becomes m times 0, which means the net force is going to be 0, right? The normal force is kind of unknown at this point, so we'll leave it like this. But we do know something about FGY. We know that it's 245 newtons. We also know that it's 245 newtons downward. So I'll use a negative for the down and 245 newtons for the value of the force. And then you see that when we bring it to the other side, we now know the value of the normal force. Notice something important. The normal force is no longer equal to our original gravity. See how the original gravity was 490? The normal force is not 490 any longer. That only happens on a level surface. The normal force is only 245. Where's the rest of the gravity force going? It's pulling down the slope. So now we can move over to our Fnet x equation. Move that out of the way. Move the mouse. Okay, so let's do Fnet x and see what happens. Fnet x. Well, if you look at the picture again, there are only two forces acting. In fact, there's only one force, I can see, acting on the x, and it is now this value. It is the other part of the gravity that's pulling us down the slope, which is our new x direction. There's simply only one force. Oh wait, my mistake. There's also friction. You can't forget our friend friction over here. We didn't put it on the picture because we weren't sure what was going to happen. In this case, it's pretty straightforward though. If there's only gravity pulling down the slope, the friction really has to only be one way. The friction has to go against the gravity. So we could add the frictional force in here and call it friction in this case, because nobody's pulling on the block, so there's no question as to which way it's going to go. It's either going to go down the slope or it's going to stay still. It will never go up the slope. And so in order for it to go down or stay still, friction has to work that way. So we'll put the friction in there now, and now we can finish our Fnet x, which is the force of friction plus the horizontal component of gravity, this way, 424 newtons. But I'm not going to put that in yet. I'm going to give it a name. I'm going to call it FGX. So it's the x component of gravity. Now we're trying to determine if there's any kind of acceleration. So we'll use Newton's law, Fnet equals ma, but we won't say it's 0 because we don't really know yet. And the force of friction is equal to mu times Fn. Mu times the normal force. Remember that from last year. And the gravity force is 424 newtons, and you'll notice that it is 424 newtons to the left. And so I will put a minus sign in front of the gravity. The mass is 50 kilograms, so I can fill that in. The mu is 0.1, I can fill that in. And I know the normal force now because I figured it out in my Fnet y equation, so I can put the 245 in there. Now, I have to make a decision about this frictional force. We said it was going to be going up the hill. So, since it's going up the hill, its direction will be positive. But if it were going the other way, which it could, this is just an example, you would have to use a negative number. So we'll leave the friction as positive, and then we'll put minus 424. And you can see what's happened. The net force equations have reduced themselves down to something with just an A missing, which means we can solve it and answer the question. So let's do that. 50A equals 24.5 minus 424. And so if we just cheat a bit, the difference between those numbers is pretty much 400, right? So we can say that's about 400 just for kicks, and then 50 over here. And you can do the actual calculator math if you want, but remember we haven't even talked about significant digits, so it's probably closer to 400. And then A would be 400 divided by 50, which would be 8 times. And so we would get 8 meters per second squared as our acceleration.
Negative, wouldn't it be negative?
And it would be negative, you're right. That's a great point. This is a negative number, so negative 400 and negative 8. And that makes sense because we're going to be accelerating down our hill this way in a negative direction. Good point, good call. Notice it's not 9.8. When gravity pulls straight down, it's 9.8 meters per second. But when it's on a slope like this, it's a little bit less than 9.8. The closer the angle of the slope is to 90, right, the closer your answer will be to 9.8, because that's what straight down would be. And as your angle gets smaller and smaller and smaller, the amount of gravity acceleration would be very minimal. So that's the simplest version of an inclined plane.